Here we are back with another video. In this lesson we're looking at further application of trigonometry. So we're at the end of this unit and we're going to be seeing how trig ratios, functions can be applied and used in real life. So if you have not already, or if you feel like you need to review basic angle of elevation word problems, I'm going to put a link here on the screen so you can go back and just refresh on that real quick, because you'll need to know angle of elevation and angle of depression, at least for the first half of this video. So let's jump right in. So the angle of elevation from the top of a small building to the top of a nearby building is 46 degrees and 40 minutes, while the angle of depression to the bottom is 14 degrees and 10 minutes. If the building is 28 meters high, find the height of the taller building. So one of the struggles with this type of problem is simply getting the picture right. So we have a small building, so there's a little small building here, and we have a taller building, so to the right of it. So the angle of elevation, so that's where we have our horizontal line, angle of elevation is this amount. The angle of elevation to the taller building is 46 degrees and 40 minutes. Where the angle of depression, that's where horizontal line, we look down, that's where we have an angle of depression of 14 degrees and 10 minutes. So in addition to this type of problem that we did not see last time is how our angles are presented to us. We have degrees and minutes here. So we desire to know the overall height of this building. So you might think, okay, if I could find this portion and this portion, I would add those two values together. And that's actually the approach we're going to take in this problem. So we know that the smaller building is 28 meters high, tall, I should say, 28 meters tall, which we can translate over here to this side. So we already know this portion of the building. Now, you're probably thinking, okay, let's just find this portion and you add it with 28. Yes, but understand with trigonometry, in triangles, I need a side length and an angle measure. So if I look at this top triangle, we have our angle measure, but we do not have a side length to help us find this side. So often in this situation, when you have two triangles that are connected, you're going to use one triangle to find the length of the connecting side, and using that connecting side will help you find the unknown length up top. So we want to find this dotted line, that we'll call it y, and then with that y we're going to find this x, and with this x we can add with 28 and get our answer. So that's our game plan right now, okay? Finding the connecting side, then with that connecting side find our x, and with the x add 28. So solving this problem. So focusing on the bottom triangle, so this is going to be y again. So we do not have the hypotenuse, so that would be tangent. We're going to be using tangent. Tangent of 14 degrees and 10 minutes equals opposite 28 over y. So in solving this, I can do two different ways of solving this. Again, how we solve this, you could have seen that in that video I posted earlier in the video here. So this is going to turn out to be y equals 28 divided by tangent of 14 degrees and 10 minutes. You can convert this 10 minutes into a decimal by dividing by 60 and then adding to 14. But our calculator, if you recall, our calculator does in fact recognize the minutes. So we want 28, in radians. Let's change that. So mode, we want to convert back to degree. So we have 28, we divide that by tangent. We want 14 degrees and 10 minutes. So 14 are angle symbol, or degree symbol's second apse. So second apse, there's our degree symbol, and then 10, again, right here is our minutes. And then closing our parenthesis, we get that the y value is approximately 110 0.9262 meters. If I'm not told how to round, I use 4 decimal places just because that gives us a good amount of accuracy. So where are we at now? We have our connecting side. Okay, with our connecting side, let's find our x. So having this length, still not having the hypotenuse, that's going to get, again, going to be tangent. And we would have opposite of the angle measure is x, and adjacent is our 110.9262. So in solving this, our variables in the numerator, so solving this, we would be multiplying our two values. So when we multiply, it would be 110.9262 times tangent of our angle. Can you still see it? Yep. So that would approximately be, going back to our calculator. So I could either go up and hit enter, and it will drop my number down, or I could just do 110.9262 times tangent of 46 second apps for degree, and then 40 second apps for minutes. Hit enter, and we get 117.5749. That's again meters. That's our x value. Okay, that is our x value. So now we have x, we can add 28 to this. So we're going to say that h, our overall height, is going to be equal to x plus 28, which is 117 plus 28. Back to our calculator. I'm just going to say plus 28, and we get 145.5749 meters. And that is the height of our tall building. So we drew a picture, we formed the game plan, and with that game plan, we found the pieces for the game plan, and we are presenting our final answer. So let's try another. So say we have this type of problem. So we notice that a model rocket is being launched from approximately 50 yards from where you're standing. The rocket is traveling 20 yards per second perpendicular to the ground, so that simply says we have a right angle, which is good. What is your observed angle of elevation? So we are looking for an angle here. What is your observed angle of elevation a minute after the rocket was launched? So a minute, but also recognize that our speed was given in seconds. So our diagram, we are 50 yards from where this rocket is being launched. And the rocket is being launched perpendicular to the ground. 20 yards per second. So after a minute, minutes is 60 seconds, that is going to be 100 or 1,200 yards. So after a minute, this is definitely not drawn to scale, but it's okay. We're at 1,200 yards. So we desire the angle of elevation. We desire this angle measure. So we have learned at this point that to find an angle measure, if I know the ratio of side lengths, to find the angle measure, we will be using inverse trig. Okay, so out of our three ratios, sine, cosine, tangent, not having the hypotenuse, that is tangent. So we are going to be using arctangent, or you write tangent -1, doesn't matter. Arctangent of opposite over adjacent. And we place this in. So we want arctangent, okay, of 1,200 divided by 50. We're still in degree, that's good. And we get an angle measure, an angle of elevation of approximately 87.6141 degrees. And it says nothing here about writing the answer in degrees, minutes, seconds, so this is perfectly fine. And that's the angle of elevation after 1 minute. And understand, if this is 2 minutes, we don't know if this is doubled. Actually, it can't be doubled if it's 2 minutes, just because doubling it will give us an angle measure over 90, and that's not possible within a triangle. Okay, so we've applied trigonometry so far. We see a problem here with inverse trig. Let's see what is next. So you are standing 150 feet from the base of a 73-foot cliff. Your friend is rappelling down the cliff. So if you do not know what rappelling is where somebody with a line climbs down a cliff. You can easily YouTube it or search it, Google it. If you do not know what rappelling is, write a model that gives your friend's distance from the top of the cliff as a function of the angle of elevation. So all of this might seem a little cloudy to you, writing a model as a function of angle of elevation. Let's just get ourselves a picture first, and that's going to help us. So we are 150 feet from the base of a cliff, of a 73-foot cliff. Okay? So with this, that's actually not drawn right. Well, mixing this a little more. So 73 feet up to here. Okay. So with this, D, our variable, represents how far he is from the top of the cliff. Okay, so from the top of the cliff, this number, this D value, is going to increase as he goes down. Okay, it's how far he is from the top of the cliff. We want to write an equation to represent the distance he is from the top. Okay, so we have this D, this unknown D, but we also have this unknown value here. But what can be said is that this distance from the top is going to be the total distance, 73, taking away this x value. Okay, so notice I'm looking towards the end of my problem. So the distance is going to be 73 minus x. Well, now I need to write x in terms of theta. Well, theta, thinking trigonometry, not having the hypotenuse, again, we're using tangent. So tangent of this theta is going to equal opposite over adjacent. So writing it in terms of x, I'm going to multiply by 150. Okay, so this x value, this distance here, is going to equal 150 times the tangent of theta. So we just said a little bit ago that the distance from the top is going to be 73, subtract this x value, which we now know in terms of theta. So we're going to write this as d, we'll put d of theta, is going to equal 73. We're going to take away from that 150 tangent of theta. So this is going to be the function that will help us determine how far he is from the top of the cliff. So I think the next question has us use this. How far from the top of the cliff is your friend if your observed angle of elevation is 27 degrees and 46 minutes? So we want the distance from the top at 27 degrees and 46 minutes. Okay, so this is going to be 73, take away 150, tangent of 27 degrees, 46 minutes. And using our calculator, we see that we can find 73, take away 150, tangent of 27 degrees, 46. Ah, that's right, your paper says 20. Forgot that I changed that. So it's 20 degrees. It's 20 degrees. Forgot that I changed that. So it's 20 degrees and enter. We get that the angle of elevation when he is, his distance from the top of the cliff is 16.12 feet from the top. The reason why I had to change it from 27 to 20 is because at 27 degrees, I'm just go ahead and change this real quick so I can show you. At 27 degrees, we get a negative number, and that should throw a red flag. If you were to take the tangent, the inverse tangent or arctangent of 73 over 150, just show this real quick, 73 divided by 150, this is going to be the maximum angle of elevation that we should have in this problem, okay? So we see here that we have a max elevation, angle of elevation of 25.95 degrees. So with an angle of elevation of 27, we are, in this problem, looking above the top of the cliff, which isn't right. So we changed it to 20, and that gave us a more realistic answer in the situation. So I could put in here, 10 degrees. What is this height from the top of the cliff at 10 degrees? Now I'd simply replace our angle that we have with 10 and reevaluate, okay? So this is just an interesting problem, having modeling a problem using trigonometry. So let's look at one more where we model a problem using trigonometry. So I'm going to call this the Ferris wheel problem. So we're going to see this a couple times right now, and over the next day or two. So this Ferris wheel problem, suppose you're riding a Ferris wheel. After everyone is loaded, the wheel starts to turn, and it takes 30 seconds to make one complete turn. Your height S in feet above the ground at any time t can be modeled by the equation we have here. So we're given this equation, okay? We have this equation. So if you're wondering how we can model a Ferris wheel ride with a trig function, we're gonna look at this right now using Desmos. I'm gonna plot here the graph and talk about it a little bit. So we can see by looking at the graph how the sine function oscillates, and how this can be used to model a Ferris wheel is the Ferris wheel goes up and down, and we notice by looking at it that at certain points, you see where the line that you see now on the graph, where the line intersects the sine function, that's the height above the ground. That's what I'm using here to represent the height above the ground. So look at that intersection. So we're going from the topmost point, and from the topmost point we descend back down to the lowest point, and from the lowest point we go back up to the top point. So that's how a sine function can be used to model the Ferris wheel. And looking at our graph, we just continually go down, then back up. And if you have ever ridden a Ferris wheel, you know that that's what happens. You go down and you go back up again. So looking at this, a couple of things. We see that at the very beginning, we are 15 feet above the ground at the beginning. And then we ascend to the topmost point, which is after 15 seconds, we're 115 feet off the ground. We descend back to the lowest point, and the lowest point we see is at 30 seconds, we're 15 feet above the ground again. So then we just cycle through. We ascend back up to 115, we descend back down to 15, and we just continue that throughout the duration of the ride. So from the graph, we saw a couple of things. First thing is that we saw what the time was to get from the bottom of our Ferris wheel back to the bottom of our Ferris wheel. And it's always 30 seconds, and that should make sense to us as one complete turn. So what is the period? 30 seconds, if you remember from our lessons before, this is the interval for one complete cycle, or in this case, one complete turn. In our Ferris wheel situation, the interval is the time frame. So we know we're going to get 30 seconds from this. Okay, but how do we get 30 seconds when we look at our model? So period, when looking at trig functions, period is going to be, we'll call this capital P, 2 pi divided by b. So when I take 2 pi and divide it by pi divided by 15, Divided by a fraction, we multiply by the reciprocal. So 2 pi multiplied by 15 over pi. Pi in the numerator, pi in the denominator, they go to 1, they cancel. So we have 2 times 15, which equals our 30 seconds. Okay, so even without looking at the graph, even without knowing the situation, from our equation we could find the period. So what does this period represent? It will take 30 seconds for the Ferris wheel, spell this right, Ferris wheel, to make one complete turn. So the shortest this ride could be, when we look at it, if we are getting on at the bottom of the Ferris wheel, the shortest this ride should be is 30 seconds. Otherwise, we're going to be stopping at some point not back at where we begin. Okay? So you have 30 seconds to make one complete turn. So what is the maximum height? So what is the maximum height that we are going to experience over this ride, during this ride? From the graph, we saw, so it takes something like 30 seconds. So we're starting, I believe, at 7.5. We're starting at 15. I'm just going to plot this right. So this is 40, 30, 20, 10. So we're right here. So after 30 seconds, we're back at our initial height. And with this, the maximum height is at 15 seconds. At 15 seconds, we saw that it's at our maximum height. How do I know this? By just these two dots. The maximum height is always between the two minimum heights. If you did not know that, it's a good thing to know. So we have an amplitude of 50. So if we had no vertical translation, our maximum height would be 50. So at 50, we're at 50 if there was no vertical translation. So with this vertical translation, that 50 that point moves up by 65. So we have our amplitude originally of 50 feet, but with our vertical shift, we now of 65, we now have a maximum height of the sum of the two, which is 115 feet. So we know from looking at the graph just a little bit ago that the sine function oscillates, which means that at our lowest point we'll ascend to the top highest point, and from the highest point we'll come back down to the lowest point, and it just cycles through, it repeats. So our minimum height, we're going to use the same thinking here. So we have an amplitude of 50. So with no vertical shift, the minimum value of our graph, if there's no vertical shift, the minimum value is 50, but it's below the x-axis, so we're going to throw a negative on here because we were below the x-axis in that idea. So then with our vertical shift of 65, we see how we got that 15 feet is our minimum height in our problem. Our beginning height was 15 feet, and the lowest point along the graph is always 15 feet. And we should know this one really quickly, the last one. If the ride ends after 120 seconds, so after 2 minutes, how many cycles will the Ferris wheel make during the ride? So very beginning, our period said it's 30 seconds for one cycle. So if I say, 120 seconds, so 30 seconds for one cycle, 120 seconds would translate to 4 cycles. 4 complete cycles. So there's no decimal, it's not like, it's 4.5 cycles. No, it's after 120 seconds, it's 4 cycles, because for one cycle, it was 30 seconds. So a lot of this stuff is really pushing us to understand how we can use sine and cosine, tangent, and trig functions just in general to apply to model different situations. We have this Ferris wheel problem, we had a repelling problem, we had the rocket problem, and we had our building problem. If you need to go back and watch the individual problems again, we're going to be looking at this more and more as we go over the next 2 days. But if you have any questions or concerns, you can always ask. Post questions or comments on the classroom. I wish you best of luck in the future with modeling and applying trigonometry.